Alrighty, we are going to talk about Coulomb's law, and I am not sure why this is not full screen. I wonder if that one, nope, that did not make it full screen. We're going to talk about Coulomb's law. I'm not going to use OneNote this semester. I think that there were too many problems with it last semester, so I'm just going to try and do everything in PDFs and upload PDFs. So, Coulomb's law, we're going to look at the integral form. The last thing we saw in class yesterday was Coulomb's law with the magnitude equation. Let's put a magnitude equation. The force is equal to K Q1 Q2 over R squared. And we talked about how that looks just like the gravitational force.
Right.
So we're going to be delving into this today. And I have like 4 slides before we get to calculus. So 1785, Charles d'Augustin, to magnify it. Charles Augustine de Coulomb. I put the wrong place in class yesterday too. Charles Augustine de Coulomb published his inverse square law discovery. What Coulomb did was he took conducting globes, and he carefully distributed charge. And like, you take 2 identical globes, and if you touch them together, you're going to have half the charge on one, half the charge on the other if they're conductors. And then he measured the strength of the force between them. And by varying how he transferred the charge, he could adjust the amount. And he determined that the force was inversely proportional to the square of the distance between the centers of the globes. Now, these are spherical globes. I'm going to right now jump to probably the last slide we're going to get to in class. Newton's synthesis. Sir Isaac Newton showed first for mass, but because the force of gravity and the force for electric charge is the same fundamental equation, if you have a spherically symmetric shell, so like a basketball where you just have the spin of the basketball,
right.
If that's spherically symmetric, then if you have a mass inside of the shell, there is 0 net force on it. Doesn't matter where it is, there's going to be 0 net force. And if you are outside of that shell, then it's going to give you the same forces you would have if you had all of the mass of that shell at its center. So when we use this equation, as shown on the screen, is technically only correct for 2 point masses, 2 masses that have 0 volume, or 2 point charges, 2 charges that have 0 volume. But in practice, if the charge is spherically symmetric, then we can treat it as if all of that charge is at the center of the sphere. So often in physics class, we're going to talk about charge on spheres, because then we can treat them like point charges. So we're taking a real object and treating it as an idealized object.
Okay.
Also keep in mind that if you are far away, a square looks like a point. Or a cube looks like a point. So it depends on how close you are, if you can treat it like a point as an approximation. So this equation is really quite generally useful. But we're going to look at the cases where it's not. Now, I have here a specification to note that this equation is only true for static charge. If the charge is moving, you have more complex things at play. You still have this, but you have other things at play as well. So what we're saying right now is static electric fields. Well, not fields yet. You haven't learned that word. Just a note on the constants. I went through and double-checked things. The speed of light was unchanged with the changes to summer in units. So the permittivity of free space, which is defined as 1 over 4 pi times 10 to the -7th times the speed of light squared, that remains unchanged as well. Because, of course, pi doesn't change this summer.
I hope not.
Yeah, that would be a little magical. And the Coulomb constant, so-called Coulomb constant, K for constant, subscript E sometimes written so we don't get confused with the Boltzmann constant, which is K for constant. So that number also should have remained unchanged because it is fixed to epsilon 0 and pi. In fact, if you look at it carefully, you're like, epsilon 0, 1 over 4 pi. So 4 pi epsilon 0 means that it's c squared times 10 to the minus 7, is that right? That should be the value of k.
C squared comes. Hold up.
If you just and then for epsilon 0, plug that in, then we're going to have the 4 pi's canceling.
Okay.
And 1 over means that it's equal to c squared times 10 to the minus 7. And then you just have the unit correction times meters per Henry. H is a Henry, which you haven't learned yet.
No.
So that should not have changed because c hasn't changed, and c squared hasn't changed. Oh, and 10 to the minus 7, I think we can agree that hasn't changed either.
I would hope not.
Yeah. So those are the constants we're using. So sometimes we will use this permittivity of free space. Permittivity of free space is a measurement telling you how easy it is to pass charge through a vacuum. And it's going to come into play today for one of the groups. They're going to determine how strong or how high the voltage is on this. And the permittivity of free space comes into that calculation. So sometimes we use permittivity of free space. Sometimes we use the Coulomb constant. The reason we change between the two is simply because sometimes it's easier to have that single constant. Sometimes it turns out when we get to Gauss's law, which we'll lecture on in this class, next class period, it's a lot easier using the permittivity of free space. But the two are tied together, so if you know one, you know the other.
Okay.
All right. So this here, I had it a PowerPoint, and each one of these would be a click forward to reveal the next bullet. So imagine you can't see anything but the top one right now.
All right.
Yeah. So Coulomb's law applies to the force between 2 point charges. Remember, I kind of emphasized that. And if you have charge spread out, then you have to add up the force between each point. Okay, so you have a fixed point here and then charge spread out here. You have to say, okay, what's the force on this due to this, and 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 then you add them all up, right?
Integration.
And that's integration. So you can see how we get to calculus on this.
Yes. And that's field, or do I still not know?
Okay, I will tell you the field right now.
Okay.
The electric field is defined as the electric force divided by one charge.
Okay.
Just like the magnetic or the gravitational field is divided by, or is defined as the gravitational force divided by one mass. Right, so you had force of gravity is equal to mg because g was the force field. So it's that force field is something you have a lot of common practice with, but the vernacular you don't have practice with.
Right.
Okay, so this equation, probably should have done some undo instead of erasing everything by hand here, or just selected everything and erased. This equation here is no different than what we had before, except one of the charges was changed to dq. So this is saying I have a point charge, q1, that's supposed to be point, in the presence of dq that is charge spread out over a region. So we're going to use this equation to find the force between a point charge and a charge distribution. Now, if you had two charge distributions, you could further generalize this and have a dq1 and a dq2 and have to do integral over both of them to calculate the force between two objects with charges spread over each one.
Okay.
No, we're not doing it. Yeah. Now, what's the difference in the left equation and the right equation?
R is cubed. And we have an R vector versus an R hat.
R vector versus R hat, squared versus cubed. They're the same thing because R hat is defined as R vector divided by R. Right? R hat is a unit vector pointing in the direction of R vector. And so a unit vector means it has a magnitude of 1. So if you take the vector and you divide by the magnitude of the vector, that gives you a magnitude of 1. So those two are exactly the same equation.
So why do we care that they're written differently?
Sometimes you'll find it easier using one. Sometimes you'll find it easier using the other. So I write them both just so you have reference. Sometimes it's going to be easier this way, sometimes easier that way. So let's get into using this. If you're going to use this, your process is first, you have to look at your geometry. If you have charge spread out over a line, then you're going to have dq is equal to a linear charge density, which I have up there as lambda,
Right.
times dl, where dl is your distance along the line. I put up there ds. Lambda doesn't have to be constant.
Okay.
For our starting problems, lambda will be constant. For the homework problems, it won't be. What does it do? It just adds a variable in your integral. So it's not like there's a fundamental difference other than the problems are easier if it's constant because you have one less thing integral. If the charge is spread out over an area, then I have a mu there instead of a lambda for the areal charge density. And then I have dA. What is dA? In Cartesian coordinates, that would be dx dy. If you're using spherical coordinates,
It's d theta.
it's going to be, well, generally, if you're doing spherical coordinates, you're going to have a fixed r, and it's going to be, what's it? R d theta times d phi.
Okay.
Or no, it's going to have another r. Maybe it's r squared d theta d phi. I have to. And if it's, it probably has a sine theta in there as well. I don't know. If it's three-dimensional, then you have rho is a charge per unit volume, and your dv now, if it's Cartesian, it's dx dy dz. If it's spherical, it's r squared sine theta dr d theta d phi. You know, you have different dv's depending on your geometry. And we will work problems in the different geometry so that, you know, it's not like, well, he said it, now let's figure out what it means.
I'm so lost right now.
Yeah. So, important thing here, consider the geometry. I probably should make my highlighter wider, which I can do. Highlight, no, I can't. Size, it's at max.
Okay, never mind.
I thought I could do it.
That's a handy tool, though.
It would be handier if I could get out of the way easier. All right, so moving on. After you've decided your geometry, you might remember in class yesterday, I said I never used the vector form of Coulomb's law. I used the magnitude, and then I used the old noggin to break things into components. So I don't use the vector form specifically, but you have to break it into components, and then you integrate each component separately. So those are words. Let's do actions.
Please.
So this here, I don't know if you've looked at, I was going to print it out, and I just completely forgot. The homework C1 that's due in, I think, 3 weeks. Homework C1, the first question has 2 parts, and one of them is effectively the problem I'm going to do now. So yeah, look it up there on Moodle. I'm actually going to give you time to look it up so you can see it. So we can compare what I'm doing. So HWC1.
Just one.
Yeah, just one, and then put the questions. The Q's apparently. Okay, so notice your instructions here. It says a semi-infinite wire. Semi-infinite means it has a starting point but no ending point.
Okay.
So it's a ray if you want to use geometry terms. And notice you have 2 options. Part A is a point that's directly above the wire. Part B is a point that's off to the side. So what I'm going to do here, I said assume that Q1 is on a line perpendicular to the end of the wire. So I'm doing part B. Part B is the harder of the two. Just, yeah.
Okay, so this is 1B.
This is 1B, yes. The only difference between what I'm going to do and 1B is my line is going to be finite, whereas 1B, it's infinite. Well, semi-infinite. So the first thing you do is you draw your picture, right?
Right.
So I have a vertical wire, and this vertical,
Straight line.
that's because I used the straight line tool. So it's a vertical wire of length L. And the origin, to follow along, to make it match 1B, the origin is the top here. So the top is 0, 0. I'm just using XY coordinate. I'm not worried about it. In fact, let me draw my coordinates. Hey, look, I'm going to use that straight line tool again. So my coordinate system is going to be like that. And then I'm going to look at the force on a particle out here at B, 0. B because it was part B, just in case you're wondering about the nomenclature. So I have this distance right here is B. And it tells me that this charge here is going to be Q1, well, better put capital Q1 to match my problem. And this one here is Q2.
Q2 is the wire.
Yeah. So there we have
The
a
whole
picture.
wire, not a point on the wire.
Right, the whole wire, not a point on the wire. And we're going to get to that. That's part of the process, is getting to that. So first I have my picture drawn out. And the next thing is, what kind of geometry do I have? It's linear. And so I'm going to have a little point here that I'm going to say is charge dq. Now, based on the information that's been given to me, I know that dq, since the charge is evenly distributed, it's going to be the total charge on that wire divided by the total length of the wire, and then multiplied by the length of this little segment. Right, I made that little box. That little box has a height dy.
Okay.
And so the charge in that little box is dq, which is the total charge divided by the total length multiplied by my tiny length.
Right.
It's just a proportionality. And of course, since dy technically is infinitesimal, then dq is technically infinitesimal. They're both approaching 0. That's the whole key with doing calculus.
Right.
So that's the first thing. We identified our geometry, and we identified then dq. And now I want to identify what force vector will I have between my point at B0 and that little charge dq. So if Q1 and Q2, we assume they're both positive. If they're negative, then when you put a negative number, it's going to reverse the direction.
Gotcha.
So we just assume they're both positive for starting. What direction will the force be at point B due to that little infinitesimal charge? Start with, is it attractive or repulsive?
Well, if they're both positive, that's repulsive.
Repulsive. And so going from here, here to here, I just made it a little longer than necessary. So I can say, that's the direction I'm going to have for my df. Now, given that direction, I'm going to be able to break it into components. But first, I want to find what the value of df is, and then we'll break it into components. So what is the value of df? It's the equation I gave earlier. I'm going to use k because it's one constant instead of having 4 pi and epsilon 0
So
times q1
over r vector times R vector.
over R squared times dq is the way I'm going to put it. Okay, so yes, I'm with you. This is not the way it was written before because it was written as a vector equation. So if we look at how it was written here, I'm using this form.
I thought we were using the other.
I am using this one. Right, you could use either one. They're equivalent.
Okay, so Q1.
Notice the minus sign dropped out because I just looked at the magnitude. So the minus sign drops because of the magnitude.
Right, because the magnitude is positive.
The magnitude of a unit vector is 1.
Right.
So that dropped out as well.
Wait, R hat is magnitude?
R hat is a unit vector, which means it has a direction and a magnitude of 1.
Okay.
So if I'm only looking at magnitude, the direction part doesn't matter, and the magnitude is 1. And so, I mean, I could have replaced it by a 1 if I wanted to, but what's the point?
Okay, so now why are we using big Q instead of little q?
That is immaterial. Because I defined it as charge capital Q1, that's why I have a capital Q1.
Okay.
It's just whatever that charge was.
So then df is going to be k sub e q over r squared.
Wow, I did a great job there. You're correct. K sub e q dq over r squared. Now, at this point, life looks good. And it seems like we should be able to solve this simply.
It does.
Uh-oh. Then the next step with it's not so simple doesn't turn out would make you feel much better.
No, it doesn't.
Okay,
This looks like a mess of stuff right now.
let's start one more thing before we get into the nastiness. I mean, into solving it, you know.
Yeah.
What is R? What is the definition of R?
R is radius.
Between what?
I'm going to say B and point. And yeah, that.
So that's why this is R and that's B.
Yep.
So in terms of Y and B, I can write that R squared is equal to Y squared plus B squared. Right? That's our Pythagorean theorem.
Yes.
I'm also going to define, well, we had dq is q squared over L dy. So I can take this equation and I have df in terms of dq and r squared, but r depends on y and dq depends on y. So I can make this so it only has y as the variable. Do you see that?
No.
No, then let me do it. Using what we have written here, I can write df is equal to k, and that should have been q1. So there I replaced r squared with y squared plus b squared. And then for dq, I'm going to put q2 over L dy. And there I have df in terms of only one variable.
Okay. How do you know which one is Q1 and Q2?
Because the problem told me that Q1 is the point mass and Q2 is the charge on the line. So it was, I know you can't see the rest of the problem right now. Here, let me scroll down. The problem told me point charge Q1 due to charge Q2 equally distributed over straight line. So that's how I know which one's which.
Okay. All right.
Although at this
Then
point,
yes. Okay.
at this point you see Q1 is multiplied by Q2, and it wouldn't matter if I had them reversed, but we do want to do things correctly and not just say, hey, it doesn't matter if I made a mistake.
So how do we know that y is the only variable, because it doesn't look like we know what b is?
Well, B is just a position. My problem wasn't as specific as your problem. Your problem says at a point, distance B away.
I'm just looking at this right now.
Yeah, I understand. My problem just said assume Q1 is on a line perpendicular to one end of the wire.
Right.
And so based on that assumption, I'm saying B is whatever that distance is.
Okay.
Whereas your problem specifies that distance is B.
Okay.
So that's df. I do not integrate this equation because it's a vector. I have to break it into components to integrate each direction separately.
Okay.
Right? Just looking at it, if I take the little piece up here, then df is pointing this way.
Right.
And if I take a little piece down here, then df is pointing up here. If I add up the magnitudes of df, I'm going to get a much bigger number than if I take the vectors and add up the vectors.
Right.
And so what I have to do is I have to say, well, what's the x component of df and what's the y component? I add up all the x components, add up all the y components, and that will give me my.
So this is going
actual
back to this Newton's second law and making that table and stuff.
Not Newton's second law in this case, but breaking into components.
Right. That's what I was talking
Yes.
about. Like the
Yeah,
whole
which is what we did with
table
that table. We broke it into components. So if we look at this, I've got my x and y directions already defined. So how do I find dfx?
dfx is just what the b portion is. You're going out in the b direction.
If we break this into components, it's going to have one that's like this, one that's like this. This is dfx. This is dfy. And so how do I find the fraction that is dfx?
I honestly have no clue.
Okay, well, if I had a vector, if I have this vector that's now shown in green because I covered up in red this part of it, how do I find the x and y components based on everything you've done in the past? Trigonometry, that's right. We defined this angle, which I'm going to call theta, and we'd say dfx is the adjacent side of a right triangle, and so that would be df for adjacent side times cosine of theta. And what about dfy?
That would be df sine theta.
Right. Ideas coming back, things that might have been forgotten in the Christmas break.
And however long we had done vectors for this stuff. It has been a while.
That's been a while. Now, I said I defined a theta. I can define theta in terms of that triangle again. So notice I have similar triangles, the dfx, dfy, df, and the y, b, and r. So I can define cosine of theta is the adjacent side, which looking at the left side is b over r, or putting in what r is, b over the square root of y squared plus b squared. So there's cosine theta in terms of y.
So then sine theta in terms of x would be at y over r. Negative y over r, yes.
Negative because I put my origin at the top of this, and with my positive y going up, that means my y's are negative values, but my thetas were positive values as defined here. I've made probably as many times as I taught this, about half the years I'll make a sign error here. So I did everything before class to make sure I squared away my sign errors. So there we have sine theta and cosine theta. So I could put those in and have, oops, let's try to be a little color coordinated.
So then for dfx, we would have df b over square root of y squared plus b squared. And for dfy, we would have df times the, I'm just going to put my negative in front. So negative df square root of y squared plus b squared.
Okay.
Except you jumped ahead a couple of steps or something.
Okay, you're right, I did. So this stuff here is without the cosine. Right, that's this right here.
Okay, yes, okay.
I just combined, I took away the parenthesis.
Right.
But then I have to multiply this by b over the square root of y squared plus b squared.
Okay.
And similarly, dfy is equal to kq1 q2 dy over L y squared plus b squared. And now we'll multiply by minus y over square root of y squared plus b squared. Now, these are integrable. We could integrate it just like it is without doing anything tricky. But you know what we do in this class? We do tricky.
Yeah.
Because doing that integral isn't all that fun.
No.
Right? Because we have 1 over parentheses y squared plus b squared and parentheses to the 3 halves. And then we have either dy or y dy on top, depending on if we're doing the x or y component. So what we're going to do now is trick. Change variable from y to theta. So I'm going to go back. I'm going to go back to the simpler forms that we have on this page. But I'm going to make some conversions. So notice I did cosine theta is b over r and sine theta is minus y over r. I'm also going to do tangent theta.
Which is negative y over b.
Right, opposite over adjacent, negative y over b. Now, taking that tangent theta equation, notice this relates theta directly with y.
Okay.
Now, of course,
We could do that with those too.
we had sine theta, it technically had y on top and bottom because y was part of r. Cosine theta had y only on the bottom there because it's part of r, but it's in a square root. So this one here is the simplest because it just has y on top.
So theta is arctangent negative y over b.
That's true, but what I'm going to do is take the derivative of both sides. So the derivative of tangent theta. Do you know the derivative of tangent theta?
I have my calculus book.
There you go. Because I'm the teacher, I had to look it up. Okay, so the derivative of tangent theta is 1 over cosine squared theta. And then we have to use the chain rule, a d theta on top. Right, because I just did d. I didn't say d theta. If I'd say d theta, it would have been 1 over cosine squared theta.
Oh, right.
But just since I said just d, it's got d theta over cosine. And then the right-hand side, that's just going to be minus dy over b. Therefore, dy is equal to minus b d theta over cosine squared theta. So that's my conversion to go from my dy to having a d theta.
Right.
And right now, it looks like I just bit myself in the tail.
It does.
Because I now have a cosine squared theta, and you're like, I don't think you made it easier, sir.
No.
But bear with me. We further have that from this equation here. If I solve that for r, I will have r equals, make it so you can see both. I'm just switching the b or the r in the cosine theta's position, so it's b over cosine theta.
Yep.
So now if we put these two relationships into df is equal to k q1 q2 over r squared times, and I got to look at what we had here. This equation that's in the red box, dy over L. That was our df. That's just a rewriting of what's in this red box.
Okay.
And, right, this here was r squared.
Yes.
And so I just put it back to r squared. Now if I make the substitutions,
Okay, Q1, Q2.
I'm going to put over L out front just because it doesn't have a Y or an R in it.
Right.
And then I'm going to have,
Times.
this is going to be 1 over R squared.
Oh, it is?
Well, I'm going to put it in. We have 1 over R squared and we have dy, so I have to put both in. So if I put 1 over R squared, 1 over R is cosine theta over B.
Yeah.
And so if I square that,
You have cosine squared theta over B squared.
okay? And then this here is going to be
The
dy, which is minus B.
theta over cosine squared theta. Okay, so you can get rid of a B, get rid of cosine squared theta,
I can get rid of 1b, and I can get rid of cosine squared theta.
and so then you're left with negative B theta over B. Okay, I'm gonna need to write this down. I'm so glad this assignment is for 3 weeks.
Oh, the assignment's big.
I know,
Yes,
and I will be visiting your office.
That's perfectly good. That's the way you should do it. So df now, I've written this, and now that's a real simple type of integral. The only variable is d theta.
Look,
I mean, you know, how easy can you get?
I mean, not much easier. Let me catch up.
Okay.
Because I'm
Okay.
Still running through my head. Breaking stuff down.
While you're writing stuff, I'm going to rewrite two equations.
Okay, yeah. All right, I got this.
Okay. So and you see that I just rewrote these because we had them before. It's not on the screen now.
Right.
So on your paper, you don't have to rewrite it. You already have it there.
It's somewhere on here.
So now I'm going to actually find f of x equals integral of df of x, right?
Right.
Equals integral of
Yeah, cosine theta.
minus k q1 q2 over L b cosine theta d theta. Now notice everything before cosine theta is a constant, right?
Yes.
So I'm going to move my integral sign so we have the constants outside.
Oh my God.
Right, I mean the constants can move through the integral sign.
That's so easy now.
It is so easy. The only thing that's left is what are our limits? You know, this is in calculus class where they say, oh, we know you can do limits, so we just do the integral. What are our limits?
You weren't given that word.
Well,
no.
we have a physical situation, and physical situations have limits.
It's 0 to y
Okay, we were integrating,
or 0 to f.
we would integrate from our lower y to our upper y.
So
Right?
0 minus L to here.
So, well, we're shifting that to thetas. So what angle corresponds with our lower y? Translation, would it be our maximum or minimum angle? This part down here would make you have the maximum angle.
Okay, wait, what?
Right? If you start at your lower y,
Right.
that's going to make the biggest angle possible here.
Okay, yes.
And then you're going to end up at, in this case, because of where we're positioned, theta equals 0. So our limits here are going to go from theta max to 0. That is, I made this sign error myself this morning when I was preparing. That's why I went through to make sure I wouldn't have a sign error in my lecture. Because always, you just want to go from 0 to theta max, right? But with our definition of y, it turns out we have to go from theta max to 0. Or you could then change the sign and make it positive k1 q2 over LB integral from 0 to theta max. But we'll leave it this.
Okay.
Now, what is theta max? Once again, looking at our picture, using trigonometry, we can say, well, theta related to y and b. So theta max, oops, that's the line. Theta max is equal to arctangent of minus y max, which was L, over b.
Okay.
Wait, did I do that right? No. Minus a minus L, so plus L. Because the y was minus L.
Yes.
So it's a plus L. Yeah, I was like, wait, that introduced another minus sign. Yeah. So that's our theta max, arctangent of L over b.
Okay.
And I have the minus and the minus is why I have the plus sign shown in there. Can you do the integral of cosine theta d theta?
That should be sine theta. Or is it negative sine theta?
No, it's sine
It
theta.
is. Okay.
So sine of 0 minus sine of theta max. Right, because you do the upper limit minus the lower limit.
Yep.
Sine of 0 is 0. And so it turns out that that is just equal to positive k q1 q2 over LB
Times sine theta max.
sine theta max.
But that's only f(x).
Right.
Now we need to do x, fy.
Now we need to do Fy.
Okay.
Now, before we do Fy, I want to tie this into your homework problem. What's the difference in what I'm doing in your homework problem?
That's a great question.
There's only one difference. It's a semi-infinite wire. It goes to infinity. So what is your theta max in that case? No.
Now you're
If y goes to minus infinity,
right.
then your angle is going to be a vertical, right?
Yes.
And so that's 90 degrees or pi over 2 radians.
Okay.
And so for that problem, your theta max is just going to be pi over 2.
Okay.
That's the only difference.
This is L is infinity and infinity over B is going to be 0.
Let's look back at the picture. If we look at this picture, if you go down to infinity here,
Yep.
then the horizontal component B is negligible compared to the vertical component of infinity.
So, yeah. So that's
And so you just have a vertical line for R vector.
Yes. Okay.
So 90 degrees. I had to point that out so when you get to it, you're not like, ah. Okay, so let's do the final one.
So all that's different is it's an integral of sine theta d theta instead of an integral of cosine theta d theta.
Mhm.
So the integral of sine theta, that's going to introduce the negative sign.
Yep, that's going to be.
So it's going to be
negative
minus cosine.
theta.
So that's going to give me a plus k q1 q2 over lb times cosine of 0, that's a 0, minus cosine of theta max. Nice. And of course, what is cosine of 0?
1.
What?
Well, shouldn't that be negative cosine of 0 and negative cosine minus cosine of 0?
No, remember, integral of sine was minus cosine.
Right.
And so we have the minus out front and the
Okay,
minus.
and you already canceled out the
Yes.
negatives. Okay.
It's important to keep track of those, right?
Yes. Okay, so you can also write it as negative k q1 q2 over lb times negative cosine of 0 minus cosine theta max. You could.
Yes, if you put a minus out front and minus, yes. I had to think it through. So there we did an example of a straight line with uniform charge distribution, and we found the force that charge is going to put on an object. This is more realistic than your homework problem, because your homework problem, how much charge would you have on an infinite wire if you have uniform charge density lambda?
Infinite.
Infinite, right. That's not very realistic.
No.
This is realistic. You can really have a wire this long with the finite charge on it.
Yeah.
But the one in your book is easier because of the limits. That's why or the one in your homework, because the limit makes it easier. Any questions about how I did that?
There will be.
There will be. Okay, now let's look at part A. If you look at part A, the difference between part A and part B is the position of the charge Q1. For part A,
It's going in the z-axis versus the actual y.
So for part A, instead of the charge being over here on the right, I'm just going to use the highlighter. The charge is going to be up here for part A.
Wait, huh? What?
Instead of being over B
Right.
and up 0,
Yeah.
it's over 0 and up A. And so you're going to have this distance here is A.
On the z-axis. Negative z-axis.
yeah, Z there, Y here.
Okay, so Z and Y are the same. Okay. I'm still
Yeah,
confused.
that problem there fundamentally was using the X and Z axis because there was nothing in any Y directions for A or B.
Okay.
I just use X and Y because we only have two and I tend to that.
Okay.
So the difference is the position. Is this easier or harder with the position straight above the wire?
Wouldn't it be easier because theta is 0?
Right. It's easier because your force is always in the same direction. You don't have an X component. You only have what I call the Y, what your problem will call a Z component. So it's already broken into components for you. You don't have to introduce a theta. And so you don't go through the substitution. You're just going to have R is equal to Y plus A. Or excuse me, A minus Y. Because the Y is going from 0 to negative. Yeah. And so it's a much simpler problem. If you can do this one, you should be able to do that one. I want to start with the harder one and let you do the easier one rather than do the easier one and let you do the harder one.
Okay.
Okay, we're out of time.
Will we be going over this for the next couple of weeks?
No, next class period, I will probably do a second example. I have a second example here, which is a circular arc of charged wire, and then we'll be going on to Gauss's law.
Oh, man. That was